Hi everyone. So I'm going to talk to you about the asymptotics of cross-validation. So this is based on joint work with Wendasu. So the cross-validation method is one of the most important and useful methods in machine learning and statistics. It's notably useful to evaluate models to estimate the risk of different estimator and estimation frameworks. However, despite its ubiquitous role in machine learning, its theoretical properties have been scarcely studied and are not very well understood. And so in the paper I'm presenting to you today, we established for the first time, under general condition, the limiting distribution of a cross-validated risk. This allows us to characterize its weight of convergence and to draw confidence intervals around the expected risk. And by doing so, we discover the rich sets of different behaviors for the cross-validated risk, even on simple parametric estimators. So this is what I'm going to talk to you about today. So to fix matters, we are going to have x1 and xn designate n different RID observation, and I'm going to write with f hat a certain estimator. And we want to study its risk, its behavior. So there's two different notions of risk that we could consider and look at. The first one is what I am going to call the conditional risk, which is the expected loss on a new observation of my estimator, conditional on my estimator. So this is the expected risk for one specific designated hypothesis. Then there's a second notion, which is the expected risk, which takes both the expectation on my new observation, but also on my training sets. And so this quantity is more useful to compare different methods between each other, evaluate a model in general, but can be maybe used in different settings for different data sets. So both are important quantities in different settings, and we consider the cross-validated risk as an estimator for both of those quantities. However, today, for simplicity, I'm going to focus mostly on the second one. It's also where the most interesting sets of behavior happens. So we don't know the expected risk, so we need to evaluate it. There's two simple ways to do that. The first one is to simply split my data set between a training set and a testing set. I am evaluating my model on my testing set. The problem with this method is that there's always half the data that is left unused for learning the estimator itself, which might be the hard part. So to try to fix this data wasting in a way, we can try to use cross-validation. So for that, I'm splitting my data set into k different folds, and iteratively, one of the folds is going to become my testing sets, and the remainder of the folds are going to be my training sets. By doing that iteratively, I can estimate k different estimates for my expected risk, and my k cross-validation risk is simply the empirical average of those different empirical risks. Very classical. Please note here that I'm going to keep on saying k-fold cross-validation, but there's no restriction on how big k can be. We also consider the case where k equal to n, and so we are, in that case, in the leave one out cross-validation setting. So an important question is, how much better as an estimator is the cross-validated risk? And can we use it to draw confidence intervals? So if all of my different splits were behaving independently, I would expect my cross-validated risk to converge k times faster than the simpler split between training and testing. And notably, I would expect, sorry, square root of k times. And so notably, I would expect the variance to be k times smaller. However, here there might be a lot of different dependence between the different estimators, notably if I'm doing leave one out cross-validation. So we require a bit more subtle analysis. So this question was studied before us, but the question that people focused the most on was the following. They wanted to bound the mean square difference between the k-fold cross-validated risk and a proxy for the conditional risk. This under stability conditions for the estimator. So there's a few things here that we wanted to improve on. Is the first one, we want to derive the exact distribution of the cross-validated risk so that one can actually draw confidence intervals. The second one was to know this exact ratio between the two mean square difference, so that you know exactly how much is k-fold cross-validation actually faster exactly. Is it k times faster or is it less than k times faster? And we also wanted to study the cross-validated risk as an estimator for the expected risk and not only for the conditional risk. So this is our general result. Here we, under certain stability condition for my estimator that kind of control how much and how my estimator depends on each individual observation. I'm going to have the k-fold cross-validated risk is asymptotically normal and it's going to converge at the speed of square root of n. And I know it's asymptotic distribution. If k grows slower than n, and so the testing set grows infinitely large, then I can also I also know the asymptotic distribution for the split risk, which is also asymptotically normal, but is going to converge at the speed of square root of n divided by k. I also know it's asymptotic variance, and so I can, as both of them are just normal, to know how much faster the k-fold cross-validation is, I can just compare the different variances. Please note here that the two asymptotic variances are not exactly the same. There's this additional element rho here, covariance rho, in the asymptotic variance of the cross-validated risk. This is coming from the dependence between the different splits. If rho is equal to 0, then doing k-fold cross-validation is like having k times more data. If rho is positive, then it's like having less than k times more data. Okay. We also deal with Berry's imbalance, and we provide estimators for sigma 1, sigma 2, and rho, so that one can actually draw confidence intervals around the expected risk. So for the remainder of the talk, I'm going to illustrate this with a few examples, all in a very classical, simple cases of M-estimators. Those are parametric estimators that are chosen to minimize the empirical risk, following empirical risk here, where psi is a loss that might be different than the loss I'm choosing to evaluate my model. For example, if I'm penalized, I'm doing the penalization on my model. In this setting, I can know exactly what the different components of my asymptotic variance are, and so I can actually study my problem also. Okay, example. Imagine that psi and L are the same loss. So I'm using the same loss to training and for evaluating my model. Then rho is exactly 0 asymptotically. And so asymptotically doing k-fold cross-validation is like having k times more data, and we have what we call full speed up. What happens if k is not, if L is not equal to psi? Very simple case here. Imagine we're doing ridge regression. So here, psi is going to be the means of the square loss plus penalization term, and L is simply the square loss. Well, then we can actually see that rho is going to be negative, and this is very surprising. It means that doing k-fold cross-validation for the ridge parametric ridge estimator is like having more than k times more data. The dependence between the different splits adds me power when I do k-fold cross-validation. This is illustrated by this simple example. Here I'm doing two-fold cross-validation, and here the speed up is the ratio between the two different variances. And we can see that asymptotically, doing two-fold cross-validation for the ridge is like having more than 3 times more data. And this is very surprising. Even more surprising. When do we have rho is equal to 0? When do we have rho being positive or negative? It doesn't depend only on the model. It also depends actually on the underlying distribution of the data I'm using to estimate things. So very simple example here, I'm doing classification. And so here, each observation is going to be drawn in the following way. With quality of 1/2, X is going to be drawn from one distribution D1 and from probability 1/2 from a distribution D2. I'm doing binary classification by simply doing LDA, and the loss I'm considering is a simple 0-1 loss. And we evaluate this for 2 different setups. So first one is we have D1 to be a gamma with parameter 10 and 0.15, and D2 to be a gamma with parameter 1 and 1. Then we observe that k-fold cross-validation, two-fold cross-validation, sorry, is like having only 1.6 times more data. So it's slower, we don't have full speed up. However, if we simply change the distribution T1 to be a gamma 110, then suddenly it's like having 2.3 times more data. And so it's like it's faster than full speed up. So this raises very interesting interplay between the distribution of the data, the model, and the k-fold cross-validation risk. So this is a summary of our paper. The main takeaway is that under general conditions, we establish the asymptotic distribution for the k-fold cross-validated risk, which allows us to A, draw confidence interval, and B, discover new surprising behavior for the cross-validated risk that were unknown until now. There has been also, please note, so there has been some follow-up work by Bale, Jensen, and Lester that relaxed somehow stability condition for the case where we were looking at the conditional risk. So the cross-validated risk as an estimator for the conditional risk, the other case that I did not present during this short talk. Thank you for having listened. In the first slide, I put a link to our paper. Thank you very much.